Okay, in this video I want to take a closer look on the tunnel effect in order to understand the concept. We won't use many formulas, so it's just another part of our big puzzle called quantum physics that we try to put together at least a little bit to have a greater picture in our mind about this new type of physics that is so much different to what we know from the classical physics. That's where we start with our example. So let's consider a football that we shoot at a wall. And what's going to happen is the football just bounces off the wall. That's not unexpected. Why is that the case? It can't pass through because the football and the wall itself consists of many atoms, and between these atoms there are Coulomb forces that repel these atoms, so that's why the football can't get through. On a smaller scale, we have seen that this is possible looking at the experiment of Rutherford, where alpha particles were shot at a very thin layer of gold. I think it was like 6 layers of atoms, so very thin. But what was seen by Rutherford was that many of these particles went through and others just changed direction. And what he found out is that the mass of an atom was concentrated in the middle, in the nucleus, and most of the space is just free, except for some electrons. But in a wall, when we have so many atoms, there's hardly any way to get through, and especially for a football with that consists of so many atoms itself, it is impossible to pass that wall. So now I want to look at another example which is a bit similar but leads us more towards the tunnel effect. We keep the football and we want to get it over this hill. That means we have to shoot it and give some energy to the ball in order to overcome this energy barrier with the height delta H. So the football needs that much energy to gain that potential energy or to overcome. And in order to do that, it needs kinetic energy. And with that equation, we can calculate the initial speed, the minimum speed that the football must have to reach the top of the hill if we neglect any other forces and friction on it. If the speed is lower than this minimum speed, it will only reach a certain height and then will fall down, back down again. Now if again we reduce the football to a quantum object, what will happen, or what can happen, is that even if the speed of the football is not big enough, it might just take this way to reach that position. And since this is if we stay with that example, we would need a tunnel for the football to get from the left to the right side. So that's why it's called tunnel effect. And indeed, the tunnel effect explains the alpha decay. So if we look at a big nucleus of an atom, the alpha particle is made of two protons and two neutrons. But we have the strong forces that act on these nucleons. So with classical explanation and physics, it's not possible that these nucleons overcome that potential barrier because there's not enough energy. Where should it come from? To leave the nucleus, to overcome the strong force. So that can only be explained by the tunnel effect of quantum physics, and that leads us to another model of the quantum object. We have seen that in the past we've been working with the particle model and with the wave model and its corresponding properties. So now we will, we look at particles and we know they have wave properties as well. And if we want to go more into detail, and I think I've mentioned that already, that we need a wave function to actually see what is happening. And a model for an object that is, like the nucleons in the nucleus, or an electron that is in an atom, that is, so it's not a free particle, but it's bound to whatever by forces to another object. And so we first of all we look at this wave function of a particle that is just moving. And if we draw that wave function, well, it looks like this. But what does it tell us? It doesn't mean that the particle is moving up and down and up and down. Especially in a case of a neutron, for example. A neutron doesn't have an electric charge, so it has no interaction with the electric magnetic field. For an electron, it was possible to imagine that the wave function is the oscillation of the vectors of these fields, but a neutron also has a wavelength, and so we can no longer use this image for the wave function. And that was a big problem. The wave function was already had already a great success in physics because some phenomena could be well explained with this wave function, and it worked for interference, for example. So the predictions of this wave function or that model, mathematical model, were proven or proved, but still the meaning of the wave function was not so easy. So there were a small group of known physicists who came up with the idea to, if we call this wave function psi or psi, to look at the square of this function. It's the magnitude because it's a complex function. And we know roughly how this looks like. It looks like this. And the interpretation of, let's do it correctly. The interpretation of the values of that psi squared function was a probability of the location of the quantum object. So in this, that's what I think we've talked about this before. So here there is a high probability to find the particle, and here it's 0. So it's kind of forbidden for the particle to be here. And now we look at a quantum object that is bound by some other object, or it's kind of forced into a certain position, trajectory, whatever. And this can be modeled by two barriers. That are higher than energy barriers. So here is the energy. And the energy is higher than the energy of the wave, or the object that is inside this, or between these barriers. But now what happens if we look at this mathematical model? Picture's not so good. Is that the probability to locate a particle is not going directly to 0 at these boundaries here, but there is an exponential decrease of the wave function. And behind that barrier, it continues. So there is a finite probability for that particle to be outside of this, let's call it potential barriers. And this can be explained by the wave function, and this is what has been observed in experiments, such as, well, the alpha decay, where there is a small possibility that these four nucleons are outside of the nucleus. And in that case, the distance between them is too big, so the strong force doesn't act anymore, but the Coulomb force does, because it's both particles are positively charged, so the alpha particles get kinetic energy and move away from the rest of the nucleus. I think that's about everything I wanna say. I have to say about the tunnel effect at this stage.